Hello again. We are carrying on talking about fields, and we're going to talk about a concept related to fields, which is called, or is the concept of equipotential surfaces. Equipotential surfaces. So, what do we mean by equipotential surfaces? Let's imagine we have a mass. Now we're talking about potentials. We can talk about both gravitational potential, and we can talk about both electric potential. There are some similarities because if you remember, the expression for gravitational potential, Vg, is equal to minus big G, the universal gravitational constant, times by m divided by r, the distance from the centre, and the electric potential, we just heard, is equal to the Ve, which is equal to K times by big Q, the charge on the object, divided by the distance from the centre, little r. So this, we can draw a point mass. Well, it's not going to be exactly a point mass, it's going to look like this. And at this point here, from the centre of, from a distance r from the centre of the mass, it's going to have a certain potential. But if I go around here, at the same distance from the centre, this point here, it also has the same potential. And this point would have the same potential as this point has the same potential, and this point has the same potential. This point has the same potential. It actually turns out that if you were to join up all the points around the point mass which have the same potential, then it makes up a circle. And I'm not very good at drawing circles, so I'm going to see if I can draw a proper circle. Let's just rub this out. There we go. So this is called an equipotential surface because all the points on this circle have the same potential. And you can then make a series of equipotential surfaces, and the convention is that the difference in potential between one equipotential surface and the next is the same. So since gravitational potential is inversely proportional to r, then the spacings between the equipotential surfaces closer to the mass are going to be tighter than when they are spread out. So it might look like this, but then the next one is going to be the change, or the difference in gravitational potential is going to be slightly bigger. So we have to go a bit further out, like this, and like this. You see they're getting slightly bigger as we go out because the gravitational potential decreases proportionally to 1 upon r. So these lines are called this, and this are all equipotential equipotential surfaces. Sometimes you might just hear them being called as equipotentials, and that is equal to spheres of constant potential. I've drawn this in 2D, but you can imagine this also in 3D. And the picture gets slightly more complicated if you have two masses in the same vicinity, and I'll leave that as an exercise for you to find out the equipotential lines for see what would the equipotential surfaces look like for the following? Two masses of equal mass, two masses of unequal or different masses, there's also simulations you can do for charges, because the equipotential surfaces of charges are similar. So an equipotential surface for a point charge is much, or positive point charge is much the same as for a point mass. What would the equipotential surfaces look like for two like charges? What would they look like for two opposite charges? How about two like charges of different magnitude? Or two opposite charges? Of different magnitude. We'll talk about that in another video. Right now I'm going to just quickly talk about the connection between potential and field. Now we're going to take the example of gravitational potential, but you can do the same with electrical potential. It turns out that if we have the graph of gravitational potential against distance, then it looked something like this. Now if we take a particular point at a certain distance r from the mass, and we put a tangent, let's just take a line here, let's take a line and put it at a tangent to this point here, then the gradient of the tangent to gravitational potential curve equals the magnitude of electric field strength. Likewise, if we'd had electric potential, the graph of electric potential, and took the tangent to the curve of the electric potential, it would give us the magnitude of the electric field strength. Sorry, this should be gravitational field strength here. With a bit more rigorous analysis, it actually turns out that electric field strength is equal to the negative of the derivative of gravitational potential with respect to distance, and electric field strength is the derivative of electric field strength with respect to distance, but you don't need to use calculus in this course, but it might be interesting to know. The last thing I'm going to talk about in this video is a special case when we have parallel plates. The electric field and equipotentials for charged parallel plates, and we may have taken this up briefly in chapter 5. Well, it turns out if we have, here's my top plate, it's positively charged, and I have a bottom plate down here, it's negatively charged, and the charges are placed uniformly across, and there should be equal number on the top and the bottom, so we don't have an then we define the distance between the plates as little d. Then the electric field goes from plus to minus, and it should be uniform. In between the plates, it's perpendicular to the plates like this. As we get to the edge of the plates, it gets slightly curved like this, and then even more curved as we go further out and gets weaker. So the equipotential lines look something like this. In between there'll be horizontal, and something I forgot to mention before, but the equipotential lines are always perpendicular to the field lines. As we go out of the plates, they will slightly curve off like this. So these are equipotentials. And it turns out the electric field between two plates is simply the electric potential difference divided by the distance between the plates. And interesting enough, if we have a thundercloud, then when the electric potential goes above 3 times 10 to the 6 volts per meter, which is the units, then we get lightning. Discharge, an electric discharge.